Here we're going to discuss the inelastic models based on additive strain decomposition. Topic is inelastic models based on additive strain decomposition. This model is for plastic materials. Plastic materials. For small strain, we can decompose the strain tensor into elastic part, elastic strain, and plastic strain. If you consider isothermal case, for isothermal case, our change in temperature would be 0. So for the process, we have no thermal influence. No thermal influence. To visualize what is a elastic and plastic strain, we need to draw a stress strain diagram. This is our stress and this is our strain. We load the material. The graph follows this path. When unloading, follows this path. As you can see that the total strain, Shalin, there is, when the material is unloaded, there is a plastic permanent deformation, which is the inelastic strain that is not recoverable. And the part of strain that is recoverable is elastic strain. The tangent of the straight line, of this part of the straight line, is called E, elastic modulus E. To model this, first step is to identify the free variables. The free variable is the total strain epsilon that is measurable. The hidden variable I is the inelastic strain, and alpha, another parameter that takes into account of the microstructural behavior. Then we have to identify the evolution equation. Alpha dot, which is a hidden variable, should depend on free variable and the hidden variable itself. Similar functional dependency goes for epsilon I. To depend functionally on epsilon I, and alpha. Then we would have our dependent variable D. We have stress and Helmholtz free energy or potential, psi. Our sigma would depend on, as it is our free variable, we know that the free variable depends on the free, it is sigma is the dependent variable. It will depend on the free variable and the internal variable. So sigma is a function of free variable epsilon and the hidden variable epsilon I and alpha. We take the derivative, and this would also be the form for psi, because psi is also a dependent variable, epsilon I, alpha. So my sigma, which is sigma of epsilon inelastic, and alpha, we take the derivative, time derivative. So what we get is delta sigma delta psi, sigma being function of epsilon I, and alpha contracted with alpha dot plus delta sigma delta epsilon I. Sigma is a function of epsilon I, and alpha contracted with alpha dot eta with I plus delta sigma delta alpha, with sigma being a function of epsilon I, and alpha dotted with alpha I. Similar expression we can get for psi dot. Psi dot would be a function of psi del epsilon. Chi being a function of epsilon, epsilon I, and alpha, contracted with epsilon dot plus del chi, del epsilon I, chi being a function of epsilon, epsilon I, and alpha, contracted with epsilon I inelastic, plus del chi, del alpha, epsilon, epsilon I, and alpha, alpha dot. The next step is to postulate the form of the free energy, epsilon, epsilon I, and alpha. So you're going to postulate the form of free energy is phi half epsilon elastic, a fourth order tensor C, contracted with elastic strain, epsilon E, plus the hardening potential, H of alpha. We call it hardening potential. We have our dissipation inequality, D minus rho chi dot plus S theta dot plus sigma contracted with strain rate greater than equal to 0, as we are considering isothermal case, so theta dot would be 0. Now we're going to plug in the expression for chi dot in this expression. So what we're going to get is rho minus del rho chi, function of epsilon, epsilon I, and alpha, del chi. It is contracted with strain rate epsilon dot plus del rho chi epsilon epsilon I alpha. This is the functional dependency of chi. Take the derivative with respect to epsilon I, contracted with epsilon I dot minus del alpha of rho naught chi epsilon epsilon I of alpha dotted to alpha dot greater than equal to 0 for all epsilon dot. Here we have to observe a thing that del rho chi del E, we can write it by chain rule, rho chi delta epsilon E contracted with del epsilon E del epsilon. This expression, it gives a second order isotropic tensor, 1. Another expression that we can observe is del rho chi del epsilon I is del rho chi del epsilon E contracted with del epsilon E del epsilon I. This would deal a negative of isotropic tensor, because remember, epsilon is epsilon E plus epsilon I. So epsilon E is epsilon minus epsilon I. So when you take the derivative of epsilon E with respect to epsilon I, we have minus of the isotropic tensor. Now, we have a theorem called Boltzmann theorem. The theorem goes like this. If you have a function d, which is of the form fxy, x dot plus g, xy, y dot greater than equal to 0 for all x dot, then what the function or the theorem says is that this is only true if f of xy is 0 and g of xy is 0. From the previous slide, we can see that our d follows this functional form. D follow the same functional form. We can write that del rho chi epsilon epsilon I alpha del epsilon I contracted with epsilon I minus del rho psi epsilon I alpha del alpha contracted with alpha dot is greater than or equal to 0. This del rho psi over del epsilon I, the derivative of the rho psi about with respect to epsilon I, same as del rho psi epsilon I alpha with respect to epsilon minus del rho psi epsilon I alpha del alpha contracted with alpha dot greater than or equal to 0. So this is the constitutive form or inequality with respect to psi. We have the form of our potential epsilon I alpha close to half epsilon E contracted with C plus epsilon E plus the hardening potential H of alpha. We take the derivative of this psi with respect to E. What you're going to get is sigma. Sigma is nothing but rho psi, where E, you take the derivative of this rho psi function here. What you get is C dotted with epsilon E. You can write is C dotted with epsilon minus epsilon I. The dissipation equality we have D is rho sigma I dot minus rho del alpha, rho psi epsilon I and alpha dotted with epsilon dot. You can plug in the expression for rho or we can plug in the expression for so D, it gets to the form sigma dotted with epsilon I minus the form of we have we can take the derivative of this function with respect to alpha. So when you take the derivative of this with respect to alpha, what you can get is the derivative of H dotted with alpha contracted with alpha dot. We're going to call this expression of minus of H dot of alpha the hardening variable. So we're going to denote Q of alpha by minus H dotted with alpha. This is called a hardening variable. So this is basically what you've done is a strain-driven model. The same can be done for a stress-driven model. We can translate from strain-driven model to stress-driven model by a transformation called Legendre transformation. That will be the topic of upcoming videos.